So we're going to start our lecture notes here with chapter 4.1, which is what is probability. So through our discussion of set theory, we have discussed a little bit more about probability than we might have thought. So we have defined already what a sample space is. And a sample space in set theory basically is your universe. So it's all of the possible simple events that could occur in a defined for a set of defined characteristics. Now, an event is a subset of a universe, so we can have many events that are based upon the same defined set of characteristics, but the simple events that occur within those events don't necessarily have to be the simplest of simple events. That's kind of hard to understand, but I think maybe as we go along that will become a little bit more apparent. And a simple event is basically like an element in the subset of the universe. So it's the simplest way of describing an outcome that there is. And a sample space is all of the possible outcomes or simple events for an experiment. And we usually denote the sample space with that capital S that we were talking about. Remember, on my typewritten notes, it's a little hard to do this, but this is typically the way that sample space is written. So we had rolling a pair of die, and the outcomes on all of those pairs of dies. So the simple event for each die, those are 1, 2, 3, 4, 5, and 6. But then when we take them as rolling them together simultaneously, they become sets of ordered pairs as the simplest events possible for the outcomes on the roll of dice. So we talk about them as ordered pairs, and the X's are going to be representing the 1, 2, 3, 4, 5 on one die. And remember, it's sometimes easier to think about this as a 1, 2, 3, 4, 5, 6 on a red die, and then a Y being a 1, 2, 3, 4, 5, 6 on a green die, or vice versa, or whatever. And they don't have to be different colors. They don't even have to be two separate die to be truthful about this. You can say, okay, what I'm going to get when I roll one die and then roll another die as well. Now, that of course is a little bit further explanation of what this sample space looks like. The possible outcomes when we flip a coin. Well, the sample space is indeed very, very simple events here. We have you get a head or a tail. So now we're going to talk about the sample space for the possible outcomes of a flip of 3 coins. And we're going to do that by thinking about, for each flip of the coin, what our simple events are. And that's where the idea of a simple event kind of comes into play in building a sample space. So the sample space itself may not consist of the very simplest of simple events, but maybe the outcomes based upon those simple events. So if I think about if I flip my first coin here, what are the simple events that can occur? Well, we saw those simple events right here. You could get a head, or you could get a tail. And then we're going to talk about the simple events that could occur on my second flip of my coin. So if I'd gotten a head the first time, again, I could get a head or a tail. Those are the simple events that are possible on that second flip of a coin. But over here, if I'd started out with the tail, I could have gotten a head or a tail based upon it. And then finally, for my third coin down here, if I would have gotten a head and then a head, again, my third coin, its simple events could have been a head or a tail, and that would have happened based upon those. And from here, I could have gotten a head or a tail based upon the 2 previous ones. And from here, based upon the 2 previous ones, I could have gotten a head or a tail. And finally, based upon the 2 previous ones, I could have gotten a head or a tail. Now, this little tree diagram helps us to see here are our base simple events that could happen on the first flip, base simple events that could happen on the second, and base simple events that could happen on the third that combine to show us this compound set of events. Now I'm going to go ahead and I'm going to erase the big S up here, and I'm going to write down for us all of these simple events. So my sample space here is going to look like I could get a head, and a head. So I would write this as a head, and a head. And then the next possibility would be that I could get a head, and a tail. So a head, and a tail. And then the next possibility would be a head, a tail, and a head. So I get a head, and a tail, and then a head. And again, you could think of these as being not the same coin flipped, but maybe I have a quarter and a penny and a nickel. And so you're flipping them simultaneously, and you're looking at what did I get on my penny, and what did I get on my nickel, and what did I get on my head as I flip those things together. And that's why you're seeing all these different outcomes. And finally on this side I could get a head, have gotten a head, a tail, and a tail. So then a head, and then a tail, and then a tail. And then over here, a tail, a head, and a head. So a tail, and a head, and a head. And then the next one, a tail, a head, and a tail. And that's what that one looks like. And finally, we're going down this last branch, so tail, tail, head. And then finally, our very last one, a tail, and a tail. And what we find are there are 8 possible simple events when we flip 3 coins simultaneously. Now this set of simple events will form the basis for finding probability later. And then later on, finally, we're going to see that we don't have to draw this tree diagram to find out all of these different possible outcomes, that we can actually use counting theory to come up with the number of possible outcomes there are and the different ways that these can happen, how many of each of them there are. So that counting theory will be important to us so that we don't have to draw these things visually. So that's how this chapter is going to develop for us. It's going to go from a little bit more touchy-feely into a bit more mathematical versions. So events. An event defined upon a sample space can then look different than basic simple events that occur underneath the event. So if we talk about all those 36 outcomes for a roll of a die, let me go up real quick here and show you those again. These were way back up here in the notes, right there. So all these 36 simple events that can occur, that's a sample space, right? Now under that sample space, we might want to define another event, and that event would be not the outcomes of a roll of a die, but now it is the sum of the outcomes when we roll a die, and that's an event based upon this sample space, but it doesn't have those simple events shown to us anymore. And so now the event would look like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And you see, no longer do you see the simple events occurring in there. And the ordered pairs that represent the sum of a pair of die when 2 die are rolled simultaneously. Likewise, now these show some of the simple events, but not all of the possibilities. All we're seeing are the ones that show us the 7. Now A and B certainly are related to one another, right? They're both subsets underneath the universe, but they don't necessarily have everything in common. And all of these events in B certainly relate to one of the events in A. So we're going to describe the event of getting 2 heads when flipping 3 coins simultaneously. So I'm going to do that right here. I'm going to change to red so we can see that. So if we did this as, let's call it event C, since how this would be A, B, and then C. So let's call this C, and we want to know of getting 2 heads when we flip 3 coins simultaneously. So when I say this, sometimes I'm not as specific as maybe you'd like me to be, but what this means is exactly 2 heads, not at least 2 heads. If I'm going to mean at least 2 heads, I'm going to tell you at least 2 heads. So you take that note, that wording to be exactly, not at least. So here we have 3 heads. That doesn't fit, right? 2 heads, not 3. So there we have 3. So we're going to put that one into our sample space. So that one's a head and a head and a tail. Or this one into our event, sorry. And then this one has 2 heads, so we're going to put that one into our event B or C. So this one has a head and a tail and a head. And then we look at the next one. No, that one's not going to work. It only has 1 head. Oh, here's another one. This one also has 2 heads, so we're going to put that into our samples, or to our event C. So we have tails and heads and heads. And then we have a tail, heads, tails, no, and a tails, tails, heads, no, and a tails, 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 no. And so that's what we're going to look at. So now let's talk about a kind of a relationship. There's not a question about this, but let's talk about a relationship here between what we saw with A and B, right? Here are the outcomes that result in a 7, and here are all the possibilities of the numbers that we get when we sum the outcomes of the roll of 2 die. Well, we could do the same thing here with our flips of coins. We could talk about the number of heads that we got. So I could even define an event D, and I could say the event D is the number of heads that I could get when I flip a coin 3 times. Well, how many heads could I get? Well, I might get 0 heads, right? Tails, 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 that's 0 heads. I might get 1 head, like this one here or this one here, so I might get 1. I've looked at all the ones here that had 2, and then there's one more possibility. I could get 3, aren't there? And so that would be kind of like our event A is to event B. So event D is to event A as C is to B. And that would be yet another example of an event that could occur under the general sample space that we came up for 3 flips of a coin. So you see there's a lot of events that can be described based upon a sample space, based upon a universe. Now, moving on, the simple events, we've done that to death, so I'm not even going to talk about that. The next thing that we're going to talk about is what I call the heart and soul of probability. So the heart and soul of probability is this. You have probabilities that range from 0 to 1, and they're never any less than 0, they're never any greater than 1. And a 0 is the probability that there's no way that this is going to occur. So you cannot get this event to occur. And that would be like the probability of February having 31 days. The probability of February having 31 days is 0. It's never going to have 31 days. That's not how it's set up. And the probability of an event equaling 1, that means that that's the only way it's going to happen. So what's the probability that December is going to have 31 days? The probability that December will have 31 days is 1. It's 100% chance. 31 days in December. Every single December has 31 days. And of course, we don't think about this and go, well, what if the universe exploded before December was over? It wouldn't have 31 days then. That most books say, okay, don't take your thinking over the top, right? If there's a less than 20% likelihood of something happening, go with the flow and say it's gonna happen, right? There's this little caveat there. So don't go on a tangent is kind of what they all tell you. So that's the heart and soul of probability. And now we're going to talk about different ways of defining probabilities, and I'm going to put that into our next lecture in defining these probabilities.